So this is the force. It's the function that tells us how the force, what the force is as you move around in space. So imagine that you're sitting out here in the room and you have a coordinate system where the center of the circle there on the floor is the origin of the coordinate system, right? And you have x going this way and y going 90 degrees to it or whatever, whatever way you want to set it up. If you start moving around inside of this coordinate system that you're in, the force would be different at different points. The force that is interacting with whatever, right? This particle experiences a force that changes depending on where it is, right? And this equation or this function tells you how that force changes. So if you're at the point 1 comma negative 4, then you can plug 1 in for x into this equation and negative 4 in for y in this equation, and it will give you a value. It will give you a vector that tells you the force at that point. And if you do that for all the points around, it will create this like field of little vectors pointing in different directions with different strengths. We actually call that a vector field, or I mean, you could even call it a force field if you want to go to science fiction literature, because that's what force fields are as well. So it's a field of different possible force values at different possible positions. And that is what this function represents. Our job, what it says here, our job is to calculate the work done if we go from one point to another point in this field. Bear in mind that at one point it will have one force, at another point it will have another force, and every point that you travel through in between will have a different force. So the force is changing as we go from one point to the next point. And this is why we have to do this using calculus. Because if you think of it practically, you think, okay, I'm going to calculate the work done to take me from 7 meters, 9 meters, in this case, the beginning point. Let's actually draw a picture of this really quick, because this will make it easier to explain. And when I say that I'm not expecting you to, to understand all the underlying theory and the underlying math completely in this, I truly mean that. We're not going to put this on the exam. This is not going to show up on an exam or a final exam anywhere. This is the kind of problem that we're going to do and do as an example in the homework, and we'll talk about the implications of it, and then we'll leave it for further study in your later classes, which you will do a lot of later. You'll see this later. You'll see things like this later when you're doing your calculus courses. You'll see things like this later in engineering, in chemistry, in physics, whatever field you end up going into. You will see it later in more detail. We're just giving you the introduction. So anyway, here's our coordinate system, x and y. In our beginning point, the point that we're starting at is, I think, we're going from 7,9 to 8,6. Okay, it's not a very long trip. So let's say that this is 7 and this is 9 up here. There's our first point. 7, 9. And we're going to 8, 6. So that would be just below this and just below this. So we're going to about this point, 8, 6. Now if we zoom in on these 2 points, we see that they're like this, right? 7, 9, and 8, 6. And we're going from this one to this one. And remember that work is equal to a force vector that can be changing times what we call a distance or a displacement vector, but we put a dr in front of it. Why do we put a dr in front of it? The reason is because that work always has to be calculated over some distance, so you have to go from one point to another point to calculate work. But you can break that distance down into little steps, and that's what the d means. We're going to break it down into little steps. Yes?
On the x-axis, you have to the left of 7 mark, but if it's 8, 6, shouldn't it be to the right?
Oh yeah, you're right. It's over here. Sorry. We're going this way. Doesn't really matter, but like the graph is not going to change how we do the problem, but you are correct in that is going that way. Oops. Dang it. You don't seem to be able to erase one of them. I'll just erase both of them and draw it again. That's easy enough. So we're going from 7, 9 to 8, 6, so it's actually out here, right? 8, 6. There we go. So we're going this way. But this thing is this d, this derivative here, means we're taking steps. And you say, well, how does that mesh with what I've learned about derivatives so far? Because when you've dealt with derivatives, you've always taken a derivative with respect to something. Take the derivative with respect to x. Well, when you take the derivative with respect to x, that is the same idea, but it's applied in a different way. If you have a function f of x, and you take the derivative of f of x with respect to x, d by dx, this dx still means little steps. This df means also little steps. But when you take the derivative with like this derivative fraction kind of thing, right? This derivative with respect to, and literally this is a division. This is a derivative of the function divided by the derivative of x. Mathematicians hate it when physicists say that. But it is true. It is mathematically true that this is this. This becomes a ratio. It becomes a slope. Because that's what ratios are. Ratios are slopes. It's how one thing changes relative to another thing changing, which is the slope of a line. If you want to think of it as a line, or the tangent slope of a curve or something like that, right? So you have some function like this. This is f as it moves along through x. X is going this direction, right? And you take little steps of it. You take little steps of x. You essentially break up this x into little dx's. And then you look to see how the height changes in df. And df dx becomes the height over the distance, or the rise over the run, which is the slope. So what this tells you is how a function changes as you move along in dx. What this tells you is we're going to be taking little steps in dr. We're just doing part of this. We're not doing two things. We're not taking steps in 2 dimensions. We're just taking steps in 1 dimension. Right? Here we're taking steps in 2 dimensions and comparing them. Here we're taking steps in just 1 dimension. Now, because it's a dr and not a dx or a dy, it means that you can take steps in whatever direction you need to, and whether it doesn't have to be a straight line, it can be a curve, it can be whatever. Because r is just my displacement. So I'm going to take steps along my displacement. In this case, my r is this line going from this point to this point. So I'm just taking little steps along this thing, just like this. Right? Each one of these would be considered a little dr vector. So in the end, I know that all this kind of theory of calculus can be confusing. But the point is that in the end, you can think of this integral as I'm going to take a little step, a little distance here, and calculate the force times that little distance. And that's going to give me the work from this point to the first step. Then I'm going to do it again for the next step, and I'm going to take the force times the little piece of distance for the next step. I'm going to do it again for the next step, and I'm going to keep doing that. And this thing adds all those little steps together, right? All those little works. You have a little work here, a little work here, a little work here. But because each one of those little works is different because it's in a different place, and we know that every different place has a different force because our force function tells us that, then we get a bunch of tiny little works that are all a little different from each other, but when we add them up, it gives us the total work as the force changes over that distance, right? So that is the idea behind this integral. Now, how do we solve it? How do we do this? Easiest way to do this problem is to recognize that in physics, our dimensions are separable. What does that mean? That means if you take a step in the x direction, the y direction doesn't care, right? Going in the x direction doesn't affect your y direction, and vice versa. If you go in the y direction, it doesn't affect your x direction. That means that dr can be split into 2 different steps. A little step in the x direction and a little step in the y direction. Right? So we break down our dr. Now, this is done in the book. This is done in the book in great detail. So let's go to the book and take a look at that. We have a nice example of it here somewhere. That's not it. Here we go. And this is actually why they do this at the very beginning of this chapter and spend the rest of the chapter not doing this. They just give you a little taste of it and then they say, okay, we're done. We're going to go on and just do algebra from here on out. So in this problem right here, where is it? In this section right here, in example 7.4, they talk about work that is done by forces that vary, forces that are going to change. So we have a variable force, and here they're going to do a curved path. Ours is a straight line path, but that's fine. It can be a curved path as well. And here they're doing a parabolic path, so they're actually telling us the equation for the path. So this path right here, which is a parabola, has an equation that relates y and x, that is y equals 0.5 times x squared. That is the equation of this parabola. That is going to tell us how y changes when x changes. If you take a step in y, or if you take a step in x, what happens in y? That's important because that's going to tell us something about our little dx dy steps. If you take a little step dx, the little step dy is going to be a little bit different than the little step dx because it has to follow this path, right? So we're going to need to know that. In our problem, we're not told that. We have to figure it out. We're told that it's a straight line path between point A and point B, and since it's a straight line, we have to figure out an equation for that line. So we'll do that in a second. Actually, let's do that right now. So let's see, back to our whiteboard here. So our path, in my case, the path goes from 7.9 to 8.6. This little line here. That means if I extended out this line to make an equation for this path, it would be a line that looked like this. That means it's going to cross through the y-axis somewhere way up here above 9. And that's important if you want to use the y-intercept form of the equation. But you could also use the point-slope form. Does anybody remember the point-slope form of an equation? What is it, sorry? No, that's actually the intercept version. So the intercept version, the one that you just said, is y equals mx plus b. In this one, b is the point where it crosses the y-axis, which is the y-intercept, right? Yeah, that's the other one. And this one is the slope in the slope-intercept form. In the point-slope form, you have y, what do they say? They say y2 minus y1 or something like this. Equals m, or m times x2 minus x1 or something like that. All that you have to know is that these two things have to be in the same order. It doesn't matter which point is the point 1 and which point is point 2. But point 1 is x1, y1. Point 2 is x2, y2, right? Either way. So we actually have 2 points. So that's good. We have 2 points. We can plug those 2 points into this equation. Actually, no, you know what? It's not. It's only 1 point you need. So one of these needs to be not a number, right? Because we need to have y and x in the equation somewhere, right? So we have y minus y1 times mx minus x1 or something like this. So you just choose one of these points and plug it into this equation. But we also have to know the slope, and we need both points for that. So the slope is equal to m equals the y's difference in the y2 minus y1 over x2 minus x1. And it doesn't matter which one is 0.1 and which one is 0.2. It'll give you the slope either way. So this is one version of this you could use for here. If you can figure out where the y-intercept is, you could use this equation to figure out the slope. But either way, that's your first step. Your first step is to figure out what is the equation of this line, right? And once you've figured out the equation of that line, you're going to get something that looks like y equals something times x plus b for an equation. And you can leave it in whatever form you want to. It doesn't matter what form it's in. But once you've got that equation for the line, kind of hang on to it. So you take your line equation and you'll equation for your line, and you'll circle it or something so that you remember it and go back and use it later. So we got that. So that gets you to this point where you have the equation of your path. You also have 2 points that you're going through, which is great, and you have your force function, which they have here. Now their force function is much simpler than our force function, but we'll get through it anyway. So how are we going to start this? We're going to start this by taking the derivative of our path function, because we need a dr. Remember that we're trying to get this thing done so that we have a dr to plug into our formula, wherever that is. It's up there, the work formula. We need a dr to plug in. And so what we need to do is we need to we need to create a derivative that is dx and dy instead of just dr. So what we do is we take our equation for our line. In this case, they take the equation for their... Sorry. Whenever I touch my mouse to my keyboard, it has a tendency to do that. That maybe I'm dreaming. It used to be the mouse to the keyboard. Every once in a while it does that. Sorry about that. Okay, so we're going to take the derivative of this. So you take the derivative of the left side, you take the derivative of y. Now this is a complete derivative. This is not a derivative with respect to anything. It's just a complete derivative. So if you take the complete derivative of y, it's just dy. However, when you start dealing with the complete derivative of x, when it's multiplied by something and the x is squared, then you have to change things up a little bit. The derivative of x is going to be x times 2, right? That's the derivative of the x squared, is x times 2. So you have to pull that 2 out in front, and then you have to take the derivative of the x by itself. This is the chain rule. Have you guys gotten to that part yet? Yeah, the chain rule. So it's 2x, and then you have to take the derivative of the x, so that's dx. So 2x dx is the derivative of x squared. The constant out in front just comes through, and you end up with a 2 times 0.5, which is just 1. So your end result here ends up looking like dy equals x dx. Okay? So dy equals x dx. They don't write that here, but they should. But dy does equal x dx. Now, how do we determine what the work is going to look like? Now we have to do a little bit of visualizing. So we're going to go back to our whiteboard. We're going to visualize taking a step along here and doing the work. So we're going to just look at this little step here. We're going to zoom in on it. The line here looks like this is our beginning point, and this is our step down to that first little piece. We're going to take a step in x, which is going to be a little dx, and then we're going to take a step in y, which is a little dy, right? So it's like we're stepping sideways and then we're stepping down, but the dy we've just learned is actually not dy. It's actually going to be something else. It's going to be the derivative of our line. Well, what's the derivative of our line? We haven't gotten to that yet. So our derivative of our line is the derivative of this equation. We take the derivative of y, which is just dy. The derivative of this thing, instead of being an x squared like it was in the other one, is just m dx, right? And then what's the derivative of the constant b? 0. So this is ours. Ours is actually much simpler than theirs. It's just the slope times dx. So dy equals m dx. Much simpler. So our step is going to be dx plus dy, or dx plus m dx. And if you go back to the book, that's exactly what they do. Each piece of work is the force in x times the d in x, or the little step in x, plus the force in y times the step in y, right? So what is the force in the x direction? What is the force in the y direction? Well, we get that from our force function. So what they've done here is they've actually spread out this dot product that we talked about into a very long mathematical thing. But the result is the same. If we go back to our problem here really quick. Here you go. Our force vector has an x and a y, I hat and j hat. So the x portion of this force, or the part that is in the x direction, is the I hat part, which is x times I hat. This thing down here goes for both of them. So if we split this into two pieces, it looks like this. It's the force, the x part of the force, or the x component of the force, looks like x times I hat over x squared plus y squared to the 3/2 power. That is the x part. The work in the x direction, the x part of the work function, is the integral, well, is the little piece of the work in this direction, we'll leave off the integral, is the force in the x direction. So it's this thing up here times dx. Right? The little piece of the work in the y direction is the y part of the force times dy, which happens to be m dx. So you have to multiply by the mass, or sorry, by the slope, dx, right? Where this is the slope. Right? So, this is dwy. And then the total work is this one plus this one. That's the dot product. When you take the x components, multiply them together, the x components, multiply them together, this is the x component of the work, this is the x component of the dr vector. Then you take the y components of the force and the y component of the dr vector, which we've converted into an x. But why did we convert this into an x? So that we could do the integral all as one in x. So we don't have to do the integral in x and then the integral in y. We've combined them so we can do the integral completely in x. We still have one more problem with this particular function, and that's the fact that there is still a y in our function. We don't want to have a y. We want to have all x's. So how do we get rid of this y? Well, we have an equation for that. We can convert any y into x by using this equation here. So we plug this equation in for y right here, and we get a new function, so a new force function. Let's see, I think that I can go to a new page here somewhere, maybe not. Oh yeah, right here. There we go. So our original force function looks like this. I hat x plus y j hat all over this cubed 3/2 squared thing, x squared plus y squared, right? And I'm going to break this down. I'm going to have an x times I hat over x squared plus y squared, 3/2. And this is a lot of writing, although there's not a terrible amount of math being done. It's just a lot of writing. So don't be too intimidated by this. Y times j hat, and remember I post these videos so you can go back and do this piece by piece, following along the video. And this is where we're actually going to start solving the problem here. So this is the x component, this is the y component, x component, y component of our force vector. Simplifying further, this one is going to change because we want it to all be in x, not y. So down here we have x squared plus, instead of y squared, I'm just going to put some parentheses there and square them. And then I'm going to do my 3/2 here. And then up here I have a y. I'm just going to put parentheses in place of that y times j hat, because I don't want a y. I want to get rid of the y. I want to keep everything in x squared plus, and I don't want y down here, y squared, so I'll just replace that with some parentheses. to the 3/2. And now I'm going to make the big replacement. In my particular problem, m is equal to -1 because my line has a slope of -1. It goes from 7, 9 to 8, 6, which is going to be a slope of -1. That means m is going to equal -1, and I don't know where it crosses the y-axis, but I can guess because I'm going to take going from 7, 9, if I go back 7 steps to here, I'm going to have to go up 7 steps from here, which is going to cross at 16, right? So my equation is going to be -x plus 16, just figuring out that equation. So I have an equation that says y equals -x plus 16 for my line. That means I can plug in wherever y was, I can put in -x plus 16. -x plus 16. -x plus 16. Okay? So now I have an equation, now I have a function that is completely x dependent. It has a y component, but the y component doesn't care what y is. It just cares what x is, because we have a relationship between x and y. So I used my path equation to turn my force equation, or my force function, into a completely x dependent. Now you could actually do it completely y dependent if you wanted to. You could rearrange this equation and solve for x. Doesn't really matter, but we did it for y. Now there's a little bit of messy arithmetic to do, a little bit of messy algebra to do. It's not difficult, it's just you want to keep track of what you're doing so you don't make a mess of things too much. But you're going to want to expand this out, this x squared thing out, into a trinomial, and then combine like terms, and then probably refactor it into something simple, right? So you're going to end up with a 2x squared on this. On both of them, they're going to be the same, right? So you're going to end up with a 2x squared because you're going to get x squared here. You're going to end up with a -32x, right? From the 16 and the minus x, and then you're going to end up with whatever 16 squared is. It's like 324 or something like that. I don't know what it is. I want to say 324. No, that can't be right. 316? I don't know what it is. Whatever it is. Plus, what is it?
256.
256. I should have known that. Why didn't I know that? 256. Okay, so we got 256. And then you're going to want to factor this. You'll factor out a 2 to begin with. You'll get x squared minus 16 plus 128. And you're going to factor that into something. I don't know what it'll be. Some number. It'll be x, minus something times 2 out in front. Whatever this is, squared. You'll use the, whatever they call that, the binomial or the quadratic formula, something like that, right? Whatever. So you're going to get this down in the bottom there, and then this thing will be raised to the 3/2 power again. There's probably a way to do it. There might be a way to factor it otherwise. I don't really know. But this is probably your best bet, because then you have what you'll have in the end is you'll have this x minus something squared, and this thing we have a formula for. In other words, we can do the integral. Once you get it to this point,
So what are you doing now?
so what we're doing here is we're essentially we're combining the x squareds down here so that we have one. So that we have one thing down here instead of two things, right?
You can't just have that 2x squared minus 32x equals 256.
You could do it this way, but this way I don't have. The thing is that this integral is going to be a little bit touchy to do. And as I've worked on this with different students, I'm seeing students' eyes glaze over quite a bit when I get to this part, which is making me really think that I should just make this class discussion, kind of a, you've had the experience, and I'll just give you the credit for the problem kind of thing. I guess that I was a little ambitious doing this, but when you get to this kind of a thing, so integrals in calculus are not easily done in general. There are some integrals that are very easy to do, like polynomial integrals. Some trigonometric integrals are really easy to do. But in fact, most functions are not integrable. You can't integrate most functions. So there are many functions out there that are very difficult to integrate, and this is one of them. So instead of actually integrating them, we actually just look them up, look and see if somebody else has done it already. Because there are books and books and books full of integrals that people have done already, and they've proven that their solution is correct. And so nobody tries to redo that. So nobody tries to reinvent the wheel. They just look it up, right? And they're usually of some different form. This particular one actually comes out quite nicely. This particular integral, where you have the integral of x over x squared plus something, which is what we're going to end up with, ends up coming out looking like 1 over the x plus something. It's really quite simple, the solution. The actual solution isn't simple, but the end result is quite simple. Oh, and it's 1 over x squared plus something to the 3/2 power. That actually ends up being something simple. The point is that the reason that students' eyes are going glassy is because if they're in calculus 1, they've not gotten to the point where they've talked about integrals enough to make that point, to drive that point home. So I think I got a little bit ambitious trying to assign this problem, but the idea is still valid. The idea that these integrals can be, first of all, you can separate them into x and y things, and then you can create a relationship between x and y to combine them into one integral, and then do the integral in one variable is still quite valid, I think. So that's why I wanted to emphasize it by putting in a problem. But I mean, I guess my over-ambition was that this required so much work to get it to that point that it's kind of losing students. So I think we'll just make this question a problem that you get the points for because you were here in class and we had this discussion. But I still want to go through the rest of it here really quick. Sorry that I'm taking so much time, but I want to go through the rest of it. So at this point, we've got this force vector now, and we're going to plug it into our vector. F dot dr becomes, because of the dot product and because of the way we've broken down this force vector and the dr vector, becomes essentially something that looks kind of like a polynomial thing, right? We end up with in the top of this thing, we end up with an x plus an mx, because this one is just x, and the y is equal as an mx plus a constant plus the y-intercept. So you end up with an x plus an mx plus whatever your y-intercept was. So this is kind of like a polynomial. It's a very simple binomial, right? You get x plus mx, or m times x plus 1 out of this, right? Plus b. And then on the bottom you have this weird thing where you have this x squared plus some weird thing down here. Oh, we also end up with a 1/2 out in front, and that's fine because it just comes through the integral because it's a constant. And then on the end of this, if we put parentheses around this, on the end of this, we end up with our dr thing, which ends up being the dx plus mdx, right? So this one ends up being a dx on this one, and this one ends up having an mdx on it. So it's just two integrals in x. This is where this is a. So we've taken something that looked very simple, but in fact was very difficult, and turned it into gone through a lot of machinations of mathematics and algebra and stuff like this, and created something that is actually just two very simple integrals that we can look up, and we get an answer out. And since these integrals are done in x, then we go from our beginning x point, which in my case was 7, to our ending x point, which was 8. We integrate between our x points here because we're all on x over here. Now remember that integrals are just the inverse of derivatives. Instead of breaking some whole into little tiny pieces, it takes a bunch of little tiny pieces and adds them together into a whole. And we're adding from 7 to 8 in this case. And so we evaluate the result of this integral, which looks like something like 1 over x squared plus something like this. And for the first one, for the second one, it would be mx squared plus, no, it would be m plus bx or something like that. But either way, you can look it up and find it, and then you evaluate this between 2 points, and you're good to go. So a very long, drawn-out process, but as far as like deep mathematics goes, I mean, I've had algebra problems that are actually much harder to do as far as working out where to go next and everything else, because I think the hardest part in this for students to really understand is how do we get from this thing to something we can deal with, because dr is not in a dimension we can deal with. And that has everything to do with the path. We take the path and we break it down into a derivative of the path, and then we know the relationship between dy and dx. We do the same thing with the function of the force, so that we end up with a force that's in x, and we end up with derivatives that are in x, and then we put together our steps. And we also have to realize that the steps, you take one step in x, one step in y, and you break it down. I want to show you one last thing that kind of shortcuts this. It doesn't make it any easier necessarily, but it kind of shows you a shortcut of what is happening. Here's our original work. The work is equal to f dot dr, right? The dot product takes the x component of f and the x component of r and multiplies them together, and the y components and multiplies them together and adds them. So this equals f of y I hat plus the x part of f times j hat dot product with the x part of dr I hat plus the x part, or the y part of dr j hat. The reason I didn't show you this to begin with is because this actually confuses people more unless they've seen the work behind the curtain, unless they've seen the magic going on behind the curtain. This then equals, because the dot product equals this times this plus this times this, this equals then fy dr of x plus f, actually let's, there we go, plus f y dr of y. Right? All we did was plug in the f of x, but we changed any y dependence to x dependence by taking the line, by figuring out the line, right? Here is the x part, but we put in this weird thing where we replaced all the y's with negative x plus 16s. We put those in place of all the y's, so that entire function was a function of x. But this right here is this. It's the x dx over this thing. It's the x part of this one. And then we did the same thing here. This right here is this part. The mx plus b times m dx. And we figured out what the x part of dr is. It's dx. And the y part of dr is m dx. We figured that out by taking the derivative of dr, right? When we took the derivative of our line function, the derivative of our path, we figured out that dy equals mdx, and that dx that the x part of dr is just dx. Right? So this, in the end, is just a simple dot product, but there's a lot of steps to get these things correct, to get these all in one dimension. Just a lot of kind of busy work, and very confusing busy work, no doubt. Even when you do this after you've taken this class and some calculus classes, you will still make mistakes doing it. And this is one of the reasons that in physics, they encourage you to work together in groups on your homework, because the thing that you miss will be the thing that he catches, and the thing that he misses will be the thing that you catch. And so you all compare your homework, you all do it together, and you say, wait, it needs to be this, doesn't it need to be this? And between, I think we had 5 people working on one assignment once for 40 hours in a class. 40 hours, one problem for 40 hours in my junior or senior year. And we never got the problem done. But everything that we had completed thus far was correct. We had been checking over it and working with each other so much, but we just couldn't get to the end of it. It was so long. But that's very common in physics, engineering, science, chemistry, anything like this. It's very common to have these very complex problems and to have to work on them together to make sure you get them correct. Nobody is above making mistakes, so don't get frustrated by it. Just learn to work together and learn to check your work and learn to write things out in very, very specific detail. Okay, so if you have any other homework questions, I will be here for the rest of the day. Yes?
I have some.
We can answer them right now. But I will be here for pretty much the rest of the day. I will be out for an hour or so, kind of in the middle of the day, but I'll be back. Did you have a question?
Yeah, I'll check or see how far off I am on the question on number 3.
I can check that.